There is a model running on a single desktop right now, 753 billion parameters, 433 gigabytes of weights on disk, served by a graphics card that holds 96 gigabytes. The model is 4.5 times larger than the card it runs on before a single token comes out, and it still produces about 15 tokens a second on that one machine, with no cluster behind it and no rented node in a data center. When I saw that number, my first thought was that there had to be a catch somewhere. A worse quantization, a cut-down version of the model, some quality sacrifice buried in a footnote. I went looking, and there isn't one. The weights are the same, and the output is bit identical to what you'd get from a setup with the whole model in VRAM. What makes it work isn't a bigger card. It's a different way of using memory you already own. It comes from an inference engine called FreeToken, published 5 weeks ago by a team that includes people who worked on VLLM and Apache Spark. I want to walk through how it works, because the mechanism is simpler than you'd expect, and then get to the number in the paper that almost nobody quoted, which is the one that decides whether this runs on your computer at all. Start with the constraint. A model's weights have to sit somewhere the processor can reach, and frontier models are enormous. Quantize a mixture of experts model down to 4 bits, and you're still looking at hundreds of gigabytes. A good consumer card gives you 24, an expensive 132. So for years, the answer has been to rent more cards, or send your prompts to somebody else's data center and pay by the token. Those are real answers, and they all rest on the same assumption. The whole model has to be sitting in fast GPU memory at once. That assumption is wrong, and it's wrong because of something already sitting in the architecture of these models. A mixture of experts model doesn't run all of itself to produce a word. DeepSeek V4 Flash has 256 experts in each of its 43 layers, and for any single token, a small router picks 6 of them. The other 250 sit idle for that token, then the next token arrives and the router picks another 6, possibly a completely different 6. Out of 284 billion parameters, roughly 13 billion do the work at any given moment, which means under 5% of the model is awake at once. The way I keep this straight in my head is a kitchen. Your graphics card is the counter, small, expensive, and everything on it is instantly to hand. Your system RAM, the ordinary memory your computer has, is the pantry down the hall. Cheap, enormous, and it takes a walk to get anything out of it. A mixture of experts model is a recipe that needs 6 ingredients out of 256, and it won't tell you which 6 until you're already cooking. The arithmetic on those 6 is easy, and the GPU gets through it in milliseconds. Saving compute doesn't save memory, though. All 284 billion parameters still have to exist somewhere reachable within a couple of milliseconds, because you cannot know which 6 the next token wants until the moment it asks. So the weights live in your system RAM, in the pantry, and the card keeps whichever ones fit on the counter. Every time a token routes to an expert that isn't on the counter, somebody has to walk down the hall. That walk is where all the time goes. It's a transfer over PCIe, the bus between system RAM and your card, and on a good desktop, it runs at around 50 gigabytes per second, which sounds fast until you notice the card's own memory runs about 20 times quicker. Moving the data costs more than doing the arithmetic on it. So every design decision in every one of these engines is really a different answer to one question. What do you do in the microsecond after the model asks for an expert you don't have on the counter? Llama.cpp has had a reasonable answer for a long time. It's the engine underneath the Llama and LM Studio, and most of the local tooling people actually run, and its answer is a configuration flag. Keep the expert weights of the first N layers on your CPU instead of your card, and run them there rather than shipping them back and forth. The important word in that sentence is N. It's a split by layer number, which means you pick the number before the model has seen a single token, and then it stays fixed for the whole run. That would be fine if routing were fixed too, but the model chooses its experts at runtime, token by token, long after you settled on your number. A split by layer index cannot see any of that. It's fast and predictable, and it runs on nearly any hardware. And it's completely blind to the one signal that decides where the time goes. So the obvious fix is to guess. Watch the routing, learn the pattern, work out which expert the model is about to want, and fetch it early. That is not what FreeToken does. And the reason it doesn't is the part that surprised me. Predicting which expert comes next isn't a new idea at all. It's essentially the whole prior art. Mixtral offloading, Mo Infinity, Promo-y, ExpertFlow, FineMoe. There's a shelf of these systems, and each one guesses better than the last. The paper's verdict on the lot of them is that they differ in how well they predict misses, but not in how they serve them. Every miss still ends up as a PCIe transfer, so decode speed stays capped by the link no matter how good the prediction gets, while the CPU sits there doing nothing. In kitchen terms, perfect prediction means you always start walking to the pantry at exactly the right moment, and it does nothing about the length of the hallway. FreeToken doesn't try to predict better. It does two other things. The first is almost insultingly simple. Keep whatever you just used. A global, least recently used cache across every layer, with no predictor and no model of the router, just the ingredients you reached for most recently staying on the counter. It works because routing has short-range locality. The expert you needed 2 tokens ago is unusually likely to be the one you need next. Not every time, but often enough that it changes the whole picture. The paper measures this about as fairly as you can. Replay the exact same routing traces through 3 different placement policies at the same cache size, so the traces and the memory are identical and only the placement changes. At the memory a 5090 can spare, FreeToken's recency cache misses 16% of expert reads on one model and 39% on the other. The policy that updates placement during prefill misses 41% and 59%. llama.cpp's static split, which the paper calls routing blind, misses 62% and 89%. At 89%, roughly 9 reads out of 10 send somebody down the hall. The second idea is the one I'd actually put on a whiteboard. When you don't have the ingredient, you don't have to carry it back. Sometimes it's faster to cook that one dish in the pantry. A missed expert is a small piece of maths. You can fetch the weights over PCIe and run it on the GPU, or you can run it on your CPU right where the weights already sit and send back the answer, which is tiny. Both work, and which one is faster depends on your specific machine. Your PCIe generation, your memory channels, whether you bought a server board or a gaming board. So FreeToken splits the misses. Some go over the bus, the rest get computed in place, and the two are overlapped, so both resources stay busy. The split isn't a constant somebody picked either. You run one command, it times your actual hardware once, and it works out the ratio for you. That's the part that matters, and it isn't a smarter guess about the future. It's a single measurement of your own hallway that gets reused for every token after it. Coming from people who spent years on VLLM and Spark, I doubt it's an accident that the central idea is measure the actual system rather than build a better predictor. That's a systems instinct rather than a machine learning one. So what does that buy you? On a single RTX 5090 desktop, DeepSeek V4 Flash at 284 billion parameters generates 22 to 25 tokens per second, which the paper puts at 1.5 to 1.9 times the strongest engine it tested against. On an 8GB RTX 4060 laptop, a 35 billion parameter model runs at 39.3 tokens per second. The number I care about more is tail latency, because that's what decides whether a coding agent finishes its task. FreeToken's worst single turn stays under 44 seconds in every configuration they tested. Every baseline crosses 150 seconds somewhere, llama.cpp peaks at 232 seconds, and K-Transformers peaks at 946, which is nearly 16 minutes on a single turn. That isn't a percentage on a chart, because agents have timeouts. OpenClaw ships with a 2-minute idle watchdog, and Claude Code's default request timeout is around 10 minutes, so a turn that takes 232 seconds doesn't run slowly, it gets killed. The paper's own framing is that tail latency is an availability boundary rather than a latency statistic, and I think that's exactly right. A good average gets you a benchmark. A good worst case gets you something you can leave running. All of those numbers come from the people who wrote the engine, though. That's normal for a systems paper, and it still isn't independent. And it gets worse in the marketing. The launch post benchmarks against a llama and claims 3 to 4 times faster, and a llama is the weakest engine on the list. The top reply on the Reddit cross post is 4 words. Comparing to Ollama, don't. Against its strongest baseline on real workloads, the paper's own claim is 1.5 to 2.3 times, so the vendor undersold its own research by picking a soft target, which is a strange thing to do to yourself. And here's the number almost nobody quoted, the one that decides whether any of this runs on your machine. Look at the hardware table in the paper, and specifically at the column next to the graphics cards. 8 gigabytes of VRAM next to 32 gigabytes of system RAM. 32 gigabytes of VRAM next to 192 of RAM. 96 gigabytes of VRAM next to 512 of RAM. Notice that only the bottom row has room for the 433 gigabytes of weights I opened this video with. That model isn't living in the 96 gigabytes of VRAM. It's living in 512 gigabytes of system RAM, and the card in front of it is a cache. Somebody tried to load deepseek V4 flash on a 3090 with 64 gigabytes of system RAM and watched the loader walk the checkpoint and quietly give up. The counter was never the thing holding you back. It was the pantry. Within a week of the paper going up, 5 independent benchmarks had appeared. And the interesting thing about them is how far apart they land. One tester on a 3090 with 64 gigabytes of system RAM got 51.4 tokens per second on the 35 billion model against 28.7 from llama.cpp, and time to first token on a 21,000 token prompt dropped from 37 seconds to 9. That's 1.79 times with no tuning, sitting neatly inside the paper's claimed range. A 5080 owner got around 100 tokens per second on a model bigger than their card. A laptop user with 8 gigabytes of VRAM got 44.5 tokens per second against 11.1 from llama.cpp on the same model. Then the other two, which are much worse. One person ran deepseek V4 on a 5090 through a real coding agent harness and logged 996 throughput samples over 68 minutes, averaging 9.66 tokens per second. Their verdict was not usable except for perhaps overnight runs. Another got 7.5 tokens per second on a cold start and 17 after warm-up. 5 results spread from 7 tokens per second to 100, and what changed between them was the system RAM, how much of it there was, and how fast the memory bus was. That's the hardware table's conclusion arrived at from the other direction. The model has to fit somewhere before FreeToken can do anything clever with it. The other thing to sit with is that the repository is 5 weeks old, with 1 release and 137 open issues. The issue titles give you the honest tour. Apple Silicon support and AMD support are both still open feature requests. The only ROCm port is somebody's fork, posted with the words, "Windows only for now, test please." There's an open issue about the desktop app being quarantined as a Trojan by Windows security. The install docs are refreshingly blunt about requirements. Linux, x86, NVIDIA, driver R580 or newer, and CUDA 13 on your path because the kernels compile on first run. There is no macOS build at all, not a slow one and not a fallback. And there's a reported crash when prefill goes past 48,000 tokens, while the paper's own benchmarks run sessions up to 65,000. llama.cpp, by comparison, is 3.5 years old, runs on 17 hardware backends, including Metal, Vulkan, and a Snapdragon phone, handles quantization from 1.5 bits up to 8, and lists Apple Silicon as a first-class citizen in its own README. FreeToken might have the better idea, but llama.cpp is the one with an ecosystem around it. Which leaves the practical question of whether you should touch it, and I think that's more useful than a verdict. If you're on a Mac, an AMD card, an older NVIDIA card, or an ordinary laptop, you're not in this conversation yet, and I mean that literally. The software will not run. Stay on llama.cpp or ollama or LM Studio because nothing in this video is a reason to switch today. If you have a recent NVIDIA card and, more importantly than the card, a lot of system RAM, this is worth testing. The hardware advice that falls out of the paper is to buy memory before you buy your next graphics card, and that isn't my line. It's from the person who watched a loader give up on 64 gigabytes. And if you run Mixture of Experts models all day with a coding agent pointed at them, you're the person this was built for. 44 seconds against 232 seconds is the difference between an agent that finishes and one that gets killed halfway through a task. I'd take twice the setup pain for that, and I'd probably spend more on RAM than on the next GPU generation. As for where this goes, I see 3 ways it plays out. FreeToken ships Metal and ROCm support, the tracker empties, and it becomes the thing you install. Or the idea wins while the engine doesn't. Somebody merges a routing-aware expert cache and a measured bus split into llama.cpp, and you get all of this inside the engine you already have. The paper names its own precedent for that. Fiddler proposed treating a missed expert as work rather than data. K-Transformers made it fast, neither is a household name, and both ideas are table stakes now. The third option is that somebody reads this paper and builds something better, which is the usual outcome in a field this young. So no, I don't think everyone will be running FreeToken in 2027. I'd be much less surprised if everyone is running the idea behind it. The launch post says you can run your coding agent against a frontier model for $0. The software is Apache licensed and free, and the hardware absolutely isn't. A 5090 costs several thousand, and a model that wants 192 gigabytes of RAM needs a machine built around that requirement. So local AI isn't really about free. What you're buying is ownership. Nothing you type leaves the room, nobody rate limits you at the worst possible moment, and nobody deprecates the model 6 months into a project you built on it. That machine from the start of this video is real. 753 billion parameters, 433 gigabytes of weights, 15 tokens a second, one desktop. It works because somebody stopped asking how to predict which expert comes next and started asking whether a miss has to be a transfer at all. For years, the answer to bigger models was bigger GPUs. This points somewhere else, toward engines that get smarter about the hardware you already own. The hallway was never as fixed as it looked. Somebody just had to measure it. If this changed how you think about your local setup, hit like. Subscribe if you want more breakdowns like this one. And drop a comment with your RAM configuration and whether you're going to try it, because I'm genuinely curious how many of you have the system memory to make this run versus how many are on the wrong side of that number. See you in the next one.